Hello everyone. In this video, I want to talk about our preference for log returns, and there are three main reasons for that. So the first reason is log returns are typically additive, right? So they are additive, and they are thus more suitable for modeling the compounding effect of financial assets over time. So let's look at what is how it is defined, and then how they're different from the simple return. So let's assume that the price of the asset can be denoted as P, right? So this means that we have the price PT to denote the price for time period T, right? And then the price can move, jumping up and down. So we have T plus 1 to indicate the price at day T plus 1, right? So we mentioned that we can define a simple return, which is in fact the percentage return. So it is defined as, so let's denoted as T plus 1 to indicate the return realized as day T plus 1, right? So first calculate the price difference, right? It could be positive, it could be negative, and then we normalize it by dividing it by the previous day's price. So this is what we call a simple return. So this is simple return. And now we introduce something called logarithmic return, or simply for log return. So it is defined by still taking the ratio of these two price points and then apply the logarithmic transformation. So this is what we call still R, and let's be at log T plus 1, right? So this is what we call the log return. And based on the properties of logarithmic function, we can rewrite it as log T plus 1 minus log P of T, right? So there are a few reasons why this is preferred. And the first reason is that it is easy to calculate the compounding effect. So let's see, I want to calculate the compounding effect, go through the compounding mechanism using the simple return. So what I need is to go from, if I were to use the simple return, I would say 1 plus R1, right? So this is the first day's return, and then I need to convert it to 1 plus R format, right? And then this is the total return I have. Then multiply 1 plus R2, right? And then all the way till the end of the investment period. So this is how we would do compounding, and you know that this essentially needs to multiply each period single return after plusing 1. Okay, so now let's do the same thing using the log return, and it is quite easy because now we just need to add all these simple returns, all these single period log returns. So in this case, I have log 1 plus log 2, right? So this is R log 2, and then etc. So by doing this, I'm actually doing the same thing. So if I were to expand the math out, so I have log P of 2 and P1, right? So it's in fact it's actually P1, P0, assuming we start from 0, plus log P2 over P1, etc., right? And then this will be equal to log P1 over P0 based on the properties of logarithmic function. They would multiply P2 over P1, etc., right? So this will cancel out, and we have the final PT over P0. So assuming uppercase T is our terminal period, right? And then this is our terminal return, and we can calculate it just by summing up the individual log returns, and you can also rewrite it more succinctly using this way. So going from I equals to 0 all the way to T, right? I can go from log, let's start with 1, right? So this is going to be I, right? Okay, so now the question is, are they the same? So is this equivalent to each other? So to convert it to make them equivalent, you can just take the exponential of this guy here, and then so they will be equivalent to each other. All right, so it's just one extra step. All right, so the key takeaway from this slide is that it is easy to do the compounding using the log return. Right. So let's look at the next point. The next point says, if we use log return, then they have a symmetrical distribution around 0 compared to simple return, right? And this symmetry essentially describes a scenario where the price goes from, say, P of t, and then the next day it goes to P of t plus 1, and then the following day it goes back to P of t, right? It goes back to P of t. So if we were to calculate the log return in the first period, then our log return will have log P of t plus 1 over P of t, right? The second period log return will give us log P of t over P of t plus 1, right? So the symmetry says that these two guys are symmetric around 0, and indeed they are, because if I were to equate them with an extra minus sign, this will be exactly correct, because based on the property of logarithmic function, I have log P of t over P of t plus 1 to the power of -1, right? So it's the same thing as if I were to move this as a multiplier, then it's the same thing as the inverse of this portion inside. Then it goes back to this one. So it's actually the same thing. So that means if we were to use log return and the price goes up and goes down following this trajectory, then our log return will be exactly symmetric around 0. So this will be the second period's return will be exactly the negative of the first period return, right? However, if we were to use the simple return, that's not the case. Right? That's not the case. So one simple example is if price is 100 at the first period, and then goes to 105, and then goes down to 100, right? So we know if we were to use the simple return, RT, and then the first period would be 5%, right? So first period 5%. But second period, this would be t plus 1. Second period, t plus 2. Now we will calculate as 100 minus 105 divided by 105. And this will not be equal to -5%. And if you were to go through the calculation, you will know this, right? So this, if you were to use the simple return, it will not be symmetric around 0, right? So that's the second reason why we prefer log return over simple return. Okay, so let's look at the last reason. So the last reason says that when we maximize the cumulative log return, and in fact we do want to do this because if we were to invest your money for some period of time, right? So this t it goes from 0 to uppercase t, and you want to look at how am I doing during the whole period. So cumulative log return is one of the metrics you will look at. So if we use a log return instead of just simple return, then the agents or the investor is inherently risk averse. So this means that we're going to be more sensitive to risks compared with normal scenario. So and then this is in fact due to the concave nature of the logarithmic function, right? So for example, if I have sim return 5%, 10% standard deviation, right? So and I have another asset also 5%, but 5% volatility. All right, so then you prefer this one if you were to use log return. But if you were to use simple return, then you have actually do not show such preference. So so this log return gives us a preference over this kind of scenario. So let's look at why that case, right? So we know that the logarithmic function, if we plot it, a simple basic logarithmic function will be something like this. So this is what we call concave, right? Concave. And Now, if it is a concave function, based on the Jason's inequality, right? So inequality condition, now the expectation of a function, right? So a function is going to be less than or equal to the function of the expected value of the input, right? So this is what we have if we were to, so let me just unify the notation here. It's going to be square bracket. It's going to be following this property, right? Following this property. So if we were to plug in f of x as the log of, so let me just rewrite. So we previously defined log of t, and it's going to be p t plus 1 divided by t plus 1, right? So p of t with a log. And then this is also equal to log 1 plus r t plus 1, right? So we know r t plus 1 is our simple return, and p t plus 1 minus p of t divided by tt. All right, so this is just another way to rewrite the definition of the log return to express it as a function of the simple return, right? If you plug in, you can verify that this is the case. So let's just use this definition here. So so I know that expectation of the logarithmic function 1 plus r is going to be less than or equal to the logarithmic of the expectation of 1 plus r, and this is a whole thing. And this again, we move the expectation inside. So expectation of 1 is just equal to itself. It's going to be log 1 plus expected value of the return, simple return, modeled as a random variable in this case. So this is what we mean by being concave. It will follow this relationship, right? And if we have this property, then it means that we're going to be more risk averse in the bad times, in sort of the downside risk. So we can argue this point from the graph of the logarithmic function. So we see that in this region, right, in this region, and let's again express r as our input, and then this is our log 1 plus r is our output, right? In this region, we see that the curve is more flat, right? It's more flat, and then there's no much ups and downs. So this means that if your return, right, your simple return is already very positive, and then we know that this is 1. If it's when the log r plus 1 plus r is 0, right? So if r is very big, it's very positive, then the resulting log return is going to be very flat. So it means any changes in r is going to be not causing a big change in the log return. All right. So that's what we observe. However, if we live inside this region, well, the return itself is negative, right? So the more negative, and then the more the higher the slope, right? So the higher the slope, and then that means that if the slope is higher, then any slight change in the return, right? Any slight change in return is going to be causing a big change in the log return itself, right? So that means that we're going to have a bigger variance, right? Bigger volatility if we were to live in this region. All right. So and then if we use this function, then it displays this sort of asymmetry, right? So this is not symmetric if we were to look at the volatility or the variance in these two regions. And then that's sort of encouraging that we are inherently risk averse, because if we were to live in this region, then it's going to be causing a big change in the log return itself. All right, so that's the third reason why we prefer the log return, and thanks for watching the video.